Thank you so much, Ben, for the warm introduction. Really glad to be here. I also walked around yesterday's poster session and really impressed by the richness of the topics and the machine learning techniques we're covering. So today, my talk is on can LLMs achieve causal reasoning and cooperation? As mentioned on the slide, this whole slide deck is on my personal website, so you can access anytime. So also just as a broader overview, in case people want pointers after the talk, my complete research agenda actually consists of two separate lines, one on causal reasoning in LLMs, the other on causally understanding how LLMs work. And we just hosted a NeurIPS 2024 tutorial with 1,600 attendees last year. And also, if you check out the video, you can also get the view of what Joshua Bengio, Bernhard Schokopf, and many other pioneer AI scholars think about the role of causality in future LLMs. Another future pointer is that we do have a long paper list of causality and NLP, as well as earlier videos as well. So starting with today's talk, the motivation is that we have been using LLMs in many different disciplines, such as using them for code generation, as many of us use Copilot and others, for robotics, for decision making, computational social science, amongst others. However, a problem does arise about reliability. If we look into the error reports on common LLM systems, we might see news such as they should suggest gluing pizza and eating rocks. When people use Gemini or amongst many other LLMs, it's really typical and not specifically targeting at someone. If you look at cheese not sticking to pizza and look for some recipe suggestions, you might get things such as, let's get some non-toxic glue, like Elmer's school glue, into the sauce to add some stickiness. So it does feel like figure out some way of how recipes are usually written, but the causal relations are not that correct. The other example is that the models might not generate these suggestions by themselves, but actually like sort of cite a website and summarize it in a slightly wrong way. Like according to UC Berkeley geologist, actually 1 doc a day keeps the doctor away. And this one is actually a summarization function on some website. And apparently maybe the Onion is not the website to look at. So the type of causal reasoning that we're trying to aim at, both for testing language models and for fixing them for more reliable reasoning, is such as like in the future, if user puts such queries, what should we decide on the causal relation? So for that, I guess yesterday we already see very nice lectures about LLMs. Just a recap, when LLMs receive a question, it usually have, just to super simplify it, it usually have 3 types of different modes. The first one is direct generation, which we usually can trust it in things such as the capital of France is, and then letting it to generate Paris. The second mode is LLM plus retrieval augmented generation, RAG, where you can usually roughly trust it on summarizing opinions and findings from trusted sources, such as maybe CDC and other websites. And the third type of generation is actually about LLMs combined with structured formal reasoning. And they will mean maybe connecting LLM to coding or connecting LLM to certain statistical tools or domain knowledge in the science subject to make sure its generation is grounded. And each of its mode has some pros and cons. The first one is the cheapest to run, just one shot. But then we face this common problem called hallucination, generating grammatically correct but semantically incorrect sentences. The second is a misinformation problem. If there are some propaganda or just scientific misinformation spread widely across the internet, then the second mode of LLM plus RAG will be attacked. The third one, which is also why we really want to emphasize on reasoning, if you look at the latest updates of language models, is really about bringing structured formal reasoning into making models more trustworthy. So one early example of like a very simplified reasoning task that models can do correct is, for example, if you ask it, what is the 17th root of 1,000? And then it will give this step-by-step answer to transform the question and also call a calculator, then deriving at the result, which is correct. Actually, before 2024 and for earlier models, it does struggle on the problem, mainly because the first mode, direct generation, cannot really solve it. So, but then for scientists, we actually need this type of step-by-step reasoning, of course, not on this simple problem and on a general set of problems. And then here, the broader scope is that we have the current skill set doing very fluent, grammatically correct direct generation, polishing our essays all the time. We have them retrieving things on websites, such as like Perplexity AI, compiling results after looking dozens of the websites. And then we face problems. Some websites might be wrong. And the third skill we want to look at is maybe we want to add some data analysis skill, maybe let the language model call certain correlation fitting or basic statistic tools. And then one case here could be that if we let LLMs to fit a statistical model when facing a data that we give it. Here's an example of like this chocolate cause Nobel Prize, where you plot each country on XY dimension, X meaning the chocolate consumption, and Y meaning the Nobel laureate per 10 million population. And then you see roughly a linear line here, fitting the data well and maybe statistically significant. And plus, we might see websites claiming eating more chocolate produces Nobel Prize winners. And of course, we can have a patch on the LLM saying that confectionery should not be a good source. But then sometimes we also have Forbes publishing some opinions, and then the articles can claim the same findings. So it will mean like a simple patch of looking at the URL domain of the source might also not be enough. So we really need a model that think like scientists, and all of the previous skills could go wrong. What could be missing? Adding causal reasoning into it. And to highlight what we mean by causal reasoning, it is that we don't just want to interpret the past, like fit in existing data very well, but we want to act towards the future. If we find something that increases the scientific research quality of a country, we want to act on it, maybe some intervention on education system, subsidy programs, and so on. And we need to understand what causes what. As early as in Aristotle's time, he emphasized that we do not have the knowledge of a thing until we have grasped its why, that is to say its cause. And just to have a more formal grounding of what we mean by causality, a common framework here is called causal graphical model, nowadays largely led by Judea Pohl, Turing Award winner. And a causal graph basically consists of a lot of random variables, in this case, X, Y, Z. And the direct edge means a direct link. Translating this into the problem we looked at before, basically the news articles or the comments about chocolate and Nobel Prize is asking whether there exists a direct causal link here. Whereas the key behind the problem is maybe there are some socioeconomic reasons and so on that leads to higher chocolate consumption and leads to higher research output. So this existence of a potential confounder causes us to confuse the correlation between chocolate and Nobel Prize as a causal relation. And just to zoom out, in the field of machine learning, we do have seen decades of work, like some of them led by Bernhard Schokopf, some of them by Joshua Bendra, and of course many researchers in the field on causal representation learning, where causality can be used for machine learning. Although my talk is mostly on language models, Bernhard and Joshua does have work, and many other scholars does have work on modeling astronomy and then judging whether there's a cause and there's an extra planet that cause certain satellite images and so on. So there are a lot of use in AI for science, physics, and many other domains. For my work, I extensively focus on causal NLP, namely understanding and improving causal reasoning in natural language processing models. And let's say that if our goal is to discover causal effects given two variables tell us our relation, what exact role does LLM serve for them? Looking into what LLMs can do, I will first cover a little bit like a literature review thing on this, and then zoom into my portion of the work on reasoning. So in general, LLMs can be used as a knowledge base, a language parser, and a reasoner. If we use it as a knowledge base, it could be things such as like common sense causality. Like there are daily cases such as the ground is wet today. What might cause it? Some people might say it might have rained, or a sprinkler might have been broken and causing the ground here to be wet. These are common sense causality. There could also be queries such as, I ran my experiment, but observed this unexpected result. Can you propose some potential causes explaining this result? These are a bit moving towards scientific causality, but more using the function of this direct generation mode, so that models are a bit like creative and coming up with commonly talked about facts. On the second direction, causality as language comprehension, basically, I guess the thing that's closest to us is this notebook LLM or Perplexity, where we can input a query, tell me the exact relation between stress and insomnia. And then this notebook LLM, or maybe we retrieve some papers and like summarize this paper. And then they might parse like condition on these patients' situation, then stress has this level of causal effect on insomnia, given some RCT study or others. So historically, this task has been positioned as a linguistics task in the beginning, namely extracting words such as leads to, give rise to, and parse them as triplets. A causes B. And it has also been information extraction, as many of our previous work has been helping medical doctors to parse their clinical notes into terms and their relations. And of course, now we have a more free-form summarizer in this field of LLM as a language parser to summarize information. The last direction that we will highlight here is LLMs for formal causal reasoning. Namely, we no longer use that as sort of a secretary for us to summarize things, but we use it as a thinker to draw a meaningful conclusion based on the statistics observed. And here we can see that it can cover a lot of different query types and skill types needed by human scientists. Just diving it deeper, actually we cover two types of LLM reasoning tasks for causality. The first task is formulated as causal discovery, namely what variable causes what. Maybe some people would be interested in whether exercising would help solve sleep quality problems. The other type, like basically they want to raise as many variables as possible that satisfies this causal relation or refute a certain misbelief. In the second category, we look into causal effect reasoning, namely, if we already know the causal graph, like X must cause Y, like stress must cause sleep quality problems, then what's the strength? And how do we measure like the actual causal relation, not confounded by maybe socioeconomic status and so on? And corresponding to some test cases that is good for early stage language model testing, we can also have daily cases, such as if language models has read a lot of news articles saying lots of tech company CEOs are college dropouts, does it mean dropout causes job success? And the other cases like COVID vaccinations, exact causal effect on survival rate. So we do have work on each of these two types of reasoning skills under our core to cause, correlation to causation paper, and Cladder paper, like climbing the causal ladder of different quantitative reasoning skills. So in the first work, can large language models infer causation from correlation at iClear 2024? We basically start from the common NLP task where models can read through a lot of common sense information. It can compile news articles. Maybe it can go through a lot of famous people's autobiography. And then like just as a test case here, we might see a case such as ice cream sales increase, the rate of shark attacks sharply increases as well. And there are two types of hypotheses we can rate. The first one is maybe ice creams make swimmers taste better. The second one is maybe it's about getting warm as a confounder, leading to people feeling hot and eating more ice creams, and also leading to more swims and thus more shark attacks. So the reason why we can sort of distinguish correlation and causation here is that if we look at maybe a desert area and remove this like C component, or maybe we put people in a place with very warm air conditioner, then maybe they also will eat more ice creams, but there's not a sharp increase of shark attacks. So what we have here is that we recall the earlier graphical formulation and put each variable into the causal graph. And then here, the common sentence that correlation doesn't mean causation actually have the following exact formal meaning. When we in natural language mention causation, C can cause D, A can also cause D. So such causation means that the two variables are on a directed path with the links all towards the same direction. Then you can say anything in the end, like an ancestor caused a descendant here. However, the reason why we refute B causes D is B includes a reversal of the causal link when it goes to D. So any reversal here will refute the causal relation. Whereas the statistical correlation still exists if you have a shared ancestor node. And then, great. Going further, so there are two ways to test causality. One is you directly intervene and put people in a different environment and get rid of C variable, then B and D are no longer correlated. Or in causality, there is also a strong statistical tool that allow us to discover causal relation without running experiments if certain conditions are satisfied, such as keep testing conditional independence tests and also running like how the data fits a certain causal graph under different conditions. So what we do here is that we put this task to large language models. And basically, the format that we wanted to perform well is we give it a bunch of correlational statements, which is similar to what we read on articles, which is similar to what we can see from like statistical testing on our CSV data and so on. And then we look at the output of the judgment of a causal relation. So such an example can be if we know A correlates with B, can we infer that A causes B? Or which has an answer of no, not necessarily. However, if we look at the case of A correlates with B, C correlates with B, however, A is independent of C, can we infer that A causes B? So the answer is yes, because A-B correlation means they have a shared ancestor, or they directly cause each other, which means the ancestor is A. B-C correlation means they have a shared ancestor in the graph. However, AC independence means they don't have anything that's shared above them, which means that they actually, so AC are independent and serve as B's ancestor. One example can be maybe the gene expression of the father correlates with the kid. The gene expression of the mother correlates with the kid. However, the father and mother's gene expressions can be more or less independent. Yeah. So with this, we introduce a core to cause benchmark and let language models do this task. So we contrasted language models' behavior before training on our training examples, like basically off-the-shelf performance, and also after training on our examples where they show a boost. So before training, just deploying many LLMs off the shelf, they're actually very close to random performance, from open source models to some closed source models. And also, like, we discovered that if a model is fine-tuned on some logical reasoning tasks, then they do perform a bit better on causal reasoning. And also, we do have seen a lot of different method follow-ups. There are usually two camps of people here improving LLMs. One camp is on scaling. So we just keep this task to still be end-to-end, input-output, and make language models go through more data, let it do chain of thought reasoning and so on, and still trust it. The other camp of people are more like they really want to plug LLMs into these code interpreters, let them execute the classic statistics algorithms. That can also increase their performance in a more controlled way. So we do see these two types of follow-ups on this core to cause task as well as different application studies deploying that to healthcare conversations, general improvement of chatbot experiences, and so on. And then also a future note, concluding this core to cause line of work, is that we do believe that future LLMs in general need more and more this type of reasoning, because we live in a world of information explosion. There can be news keep coming every day. For an LM that has read all these articles, either in the training corpus or in its web retrieval process, it needs to distinguish what causes what and what people claimed is not true and so on. So we do look forward to making this line of work more prominent in AI for science and also in AI for society. Yes. Totally. So the question is about whether old school knowledge graphs, maybe not old school, but knowledge graphs can enhance LMs. I think that is definitely a way, because in our literature review, we mentioned LLMs as a knowledge base, LLMs as a language parser, and LLMs as reasoning. They can actually be stacked upon each other. Maybe we can bootstrap it as LLM as a previous like knowledge base and know a bunch of facts. And then the language parser or like external knowledge base, so to further correct its previous belief, either from newly parsed literature or from a human well-curated knowledge base in certain domains. And then further a little bit more, if we have new experimental data, then we can fix the certain edges to make it more precise. So we're really thinking about a combined effort to push the frontier of science. Very good question. Yes, one more, and then we proceed. Yes. That's definitely a more advanced version of causal discovery. I think in this work, we assume the DAG, a cyclic graph. For cyclic graphs, A causes B, maybe stress causes insomnia, and insomnia causes next day stress. There are dedicated further causal discovery algorithms, or if you roll it out, it's actually yesterday's stress caused tonight's sleep, and tonight's sleep caused tomorrow's stress. Yeah, so there could be some way of solving it, but it's an active research direction. Awesome. So the second main task of causal reasoning that we look at is causal effect reasoning, namely by how much does an increase in X cause some difference in Y. So what we have here is both a data set and an improvement of models' causal reasoning skills. Just to contextualize this a little bit, why do we need quantitative reasoning? Why is it not just a binary relation? A has a causal relation on B, done. So one example here could be, is the causal relation positive or negative? We need an exact number. So if we look at the statistics of Israel 2021 August on patients of COVID-19, we actually see that by that snapshot of data, vaccinated people are more likely to develop severe diseases of COVID by correlation. And then does it mean that the overall causal effect of vaccination is negative for health? So what we have here is, again, we ground it in causal graph. There is a vaccination variable and a severity variable of their health condition. And then the key point here is that there exists a confounder of vulnerability, maybe amongst others. And then what happened here is that the originally more vulnerable group has a higher vaccination rate, this arrow, and also has a higher severity rate if they get COVID. So the right approach, so maybe the correlation just means that there's a disproportionately high set of vulnerable people visiting Israel's vaccination stations at that point, and thus we see such negative correlation. So the right approach here is to separate the vaccination effect for each vulnerability level, maybe stratify them, and then aggregate the data. And this is so-called confounder adjustment across statistical literature, and causality literature. So what we do here is that we compose similar problems by extracting such problem prototypes from famous causality books and also application-related papers. Then we have a large-scale data set for LLM, sort of serving as a playground to check and make LLMs improve their causal reasoning skills. So in this playground, we control the real causal effect and just check whether LLMs can perform the right type of reasoning. So we basically give it three types of informations. The first being the causal graph, the second being the available statistical relation, maybe the portion of people who are vulnerable versus not, and also condition on healthy and vaccinated people, the fertility rate being 1% and many others. Then we pose the causal query, does vaccination lead to an increase in the survival rate, increase or decrease? So we actually also extended, because the long-term goal is to really push out a causal science assistant. So we injected a lot of queries that cover correlation, like the actual relation being a correlation, interventional causality, and counterfactual causality, as well as the ground truth causal graph can be a hidden confounder or maybe a mediation, being that some people might think walking their dog outside causes their health to improve, but maybe it goes through a mediator of their sunshine, or maybe it goes through the mediator of they actually exercised when walking their dog. And then we also have things such as like given the same causal graph, then we can still come up with different variables to test whether models are robust across different types of discoveries. And then here, the long-term goal is really, if we give models sufficient statistical information and pose a causal query here, human causal inference scientists might be able to conclude the quantitative causal relation. And we want to see how close are LLMs to that extent. So I think the early model results, let's say the random baseline being 50 yes, 50 no, then a bunch of open source models and GPT-3 are close to still being random. And then the later instruction tuned models have increased results on this specific task. And further, the later model improvement have another boost. Moreover, we look into a structured way to improve models' causal reasoning that's added on to GPT-4, but it can also be added on to any LLMs. Namely, we propose this causal chain of thought, causal COT reasoning, that takes in the query with all the information and a causal question, and construct a 5-step reasoning process from parsing the right causal graph, therefore, and also formalizing the query to average treatment effect of X on Y. Then it can be represented in statistical formula, like we want to check the expected value of Y, given that we perform this do intervention on X variable, like vaccinated or not, and check the survival rate difference. Then there is statistics collection. In this work, we directly summarize the statistics, but now we also have an extension that you can plug in a CSV file where the model directly calls Python code interpreter and so on to calculate these marginal distribution, conditional distribution for you. Then we plug it in to estimate this formalized query through things such as confounder adjustment, which is a special form of do calculus, and arithmetics, like calculating the actual multiplication and addition before deriving at the final answer. So with this, after we instruct the model to do causal reasoning in this way, given controlling for the base model, we reach an 8% accuracy boost. And also we tested on a small scale with graduate students, reaching around 80% accuracy on this. Yeah, and then further, we want to see if we want to have a stable, trustworthy causal AI assistant, then actually maybe we want to aim at close to 100% accuracy. We still haven't achieved it, but we show a clear roadmap in this follow-up paper, Causal AI Assistant, SAYA, facilitating causal data science with LLMs. So what we do here is that we take the previous 5-step framework and change it from just prompting the model, leading it to think about the first step, you should do this, the second step, you should do that, to like, you now have the power to connect with Python code. You now have the power to look up the statistics sort of pathways to derive at the right choice of the statistical method and so on. So what we really look at is we want to make this step a formal causal inference, given a professional statistician skills to be more accurate. How do we do that? So as mentioned, we generalized the input to not only summarize the statistics, but a raw CSV file with maybe a treatment variable, some covariates x1, x2, x3. This is a little bit like a patient data taking a certain treatment or not. And then we look at a causal question such as how much does vaccination help? So we run our SAYA causal AI assistant framework to aim at 2 types of outputs. The first type being, have we chosen the right method to estimate it? The second is, do we derive at the right causal effect, such as taking the vaccination on this population leads to 4.02 percentage of survival rate increase, things like that. And to make our model work, we do have a selection mechanism on what exact query are we doing, what exact statistical method should we use. Then we also have a code generation. Then, given that we want to run this method, inputting the CSV file, how do we actually run the statistics? And then execute it. Plus, we also have a data science workflow breakdown to double check that everything is correct, all the assumptions are met, and so on. And the reflective analysis to further boost the model accuracy, making language models self-reflect, look at all your past steps. Are you really sure each one is correct? So using this all together, and also we will extend a little bit on how we do a method selection. So we basically, similar to a human statistician, if you go to statistics department for consultation, we have this huge tree that is not fully shown in the graph, but we have a huge tree of many branches. And it's actually a decision graph where we check is it a randomized control trial RCT? And then if yes, then we further go down, saying like, should we include the control covariates? And for sure, a lot of subjects use linear regression with the covariates that they want to control for. Or if not, if we don't care about that, people just look at the difference in means. We also have another large branch in, if we don't have RCT, then within observational data only, what can we do? And one example of that is if certain assumptions are checked, then we can run instrumental variables to still get the causal effect, even if we don't know all the confounders. So here we have this method selection mechanism before the models say that I want to execute code to realize this method. And then with this, in the reflection, yes. This is a great question. And actually, during this study, we touch upon a lot of, like, if we actually extract an economics paper, they might also have several methods for their choice. And sometimes human scientists have a preference. For our setting, we do allow multiple paths. For the model, we do allow them to select multiple paths, and they are always marked correct if the assumptions are met. Great question. Yes. And then in the reflective analysis node, like mode of the pipeline, we further enhance it by veridical data science by Bing Yu and her collaborators, actually a Berkeley professor in statistics. And the main spirit here is that we need to further simulate the workflow of expert data scientists, consisting of multiple steps in the reflection. For example, when we formulate the problem, we need to make sure the model answers a checklist of questions at each step. So our code is open sourced, and you can also check the common practice for human scientists for veridical data science. So we basically implement it for LLM scientists, making the model answer a checklist of questions at each step, such as what is the domain question, how do differences in the formulation affect the final result? Second step being cleaning the data, pre-processing. What should we do exactly in this column? Should we fill in the missing data with an estimated value or just remove this data column and so on? What are the types of such data? Exploratory data analysis could be trying the correlation analysis among every pair of columns or conditional independence tests and so on. Then in the coding step, to make the code execute with more accuracy, we actually put it in a loop of you generate a code, you also execute it like letting the language model execute it. Then check, is there a compilation error? Is there like certain outputs that's not desired, and so on. So a reflection step actually also improves the code generation quality. We also call for the model to come up with refutation methods, like doing sensitivity analysis on the parsed results. And also there are post hoc analysis, such as specify the null hypothesis, do we have enough statistical power to refute it, and so on. As well as interpretation of the results, like should we stop at claiming it just as correlation, or there is strong enough causal evidence? What recommendations to be drawn if a general public is looking at the result and want to take some maybe life tips on how to improve their health? So what we see here is that we basically checked based on the same language model. If we have just a baseline of naive prompting and don't connect model with code and all these grounded formal steps, we check their method accuracy. Is it selecting the right statistical method? And also the mean relative error on maybe the ground truth result is 4% average treatment effect, and you derived at 6, then there's a certain relative error here. We show that our SIA method has clear improvement over all of them. And in the upcoming 2 months, we are trying to put more research engineering efforts to clear out all the trivial engineering problems by language models, maybe making small mistakes. And we will try to aim at as high as possible method accuracy before introducing SIA to real data scientists and interdisciplinary scholars. The takeaway here, before we proceed to the next topic, so that we will cover in this talk, the takeaway on all the 2 types of causal reasoning and different progresses is that we really like to treat any given problem to LM as how a human scientist do. Understand the problem, ground it formally. Give me the exact formula. Tell me what variable are you looking at? How do you define these variables? Design a set of structured steps, like we need to also identify all of these, come up with all the confounders and stuff and control for them. Then use LLMs to connect with tool use, then deliver scientifically grounded results. And generalizing this a little bit to like sort of, if we have a blue sky on if our future generation growing up as young kid encounter chatbots, what does a causal reasoning chatbot mean to the future generation? So we actually have a vision for in like helping human general curiosity by causal reasoning. In this work, we sort of also think about, if we look at the Starry Night, then what are all the questions, causal questions that pop into us, even like out of the textbook? Some people might be bothered by their career questions, such as, was I rejected because I lack experience? Like it also happens in all our career stages. Or before doing PhD or deciding whether to dive into research further, should I get it or not? What causal effect does it have for my life? Or if we are just curious in general, I observe the nature changing around me. Why exactly do apples fall? And for people aiming at, or maybe just with goodwill, like how to make the world a better place, how to make the community around me a better place, and how are today's actions influencing what will happen tomorrow. So here, actually, we have a work here on parsing questions so that a future chatbot know that its causal reasoning unit should be activated. And there is an interesting linguistic behavior phenomena here. look at all these questions. At first, before I do this project, I also thought that causal questions mean why. People might explicitly ask why. However, the second keyword is how. And every how question is actually about the user give you a goal they want to achieve and ask you what are the effective causes to achieve that goal. Or in some cases, they list a set of things, a set of potential causes, different actions, and then asking you like the future projection. And then there are a lot of also like yes, no questions where they already give you like this, was I rejected because I lack experience? Here, the user also already give the chatbot, I suspect this variable A causes the variable B. Can you confirm the positive relation as I suspected for me? Or the user might have an open-ended question. They provide you the cause, getting a PhD, and they might need two steps. The first step, infer the effects that the user care about, such as does this person care about the income raise or happiness raise and many other things, maybe immigration status and so on. And then the model needs to infer a distribution of things the user care about, then get the causal effect on maybe some prominent items there. According to this survey, or hopefully the models, I read through all the LinkedIn data. And let me tell you, if you get a PhD in this region from this university, on average, the job outcome has this type of change. Our hope here was also like on academic career paths. Maybe the model can read enough websites and conclude concrete career advice, because all the researchers' trajectories are relatively open on the internet. So these are just really blue sky wishes. And our first step is that we can make this very strict statistical pipeline work out. And also we have a question parser. Then we look into how to make other diverse type of causal questions be solved. That's an open question. But here we actually have a question-specific function for language models where we build a formal taxonomy of what type of questions does there exist. And categorizing them into two big categories, where the middle two, the second and the third, are actually what we have already been familiarized in the beginning of the talk. What affects what and by how much. And then the thing here is that there actually also, if we look at the history of science in the past several thousand years, there also exist questions on what variables are there. Do we buy in Aristotle's view of air, earth, and these like elements, or can we make the variables more precise? And also, like, if we want to make a rocket into the sky, then we need a little bit more full understanding of how things work. That's also how human civilization advances, how accurate subjects in STEM actually get progressed. And then here, what it essentially means is that we have causal questions asking about the variables, asking about the edges, asking about a rough information of the edge, such as one number quantifying the causal effect, or a fine-grained information, such as give me the exact causal formula here in the mechanism. And here, like they correspond to different questions that a chatbot can totally receive, like what's the change of my income after the PhD as a type 3 question. Does smoking interfere with the drug effect? Like just a binary confirmation as the type 2 question. A type 1 question could be, what are the key elements needed to start a fire? Or for career, what are the key skills needed to become a professor? And also maybe more quantified things. I put a super naive example of like a chemical equation, then get me the exact formula and tell me how much oxygen is needed to oxidize 1 kilogram of mercury. Bring this forward. I guess we have some formulation here, sort of talking about in details what exactly we mean. by each 4 of the categories. And we also give these instructions to language models so that they can accurately like receive a question first route. Is it causality? Within causality, which of the 4 types are they? And then after that routing, they can go into, if we are asking about the causal effect, if we're asking about the edges, then we can route to a similar function as core to cause. If we're asking about the causal effect, then route to our SIA or COT, causal COT. And then for variables and mechanism, I actually really like the questions before. The current best way is still using LLMs as a knowledge base or let it to query existing knowledge graphs or read literature. But we very much look forward to breakthroughs in what is a way to propose variables that make sense. What is a way to have the next Newton, maybe still human and assisted by AI, that propose a mechanism that is correct. Like that is an advancement of their previous generation of scientists' belief, and maybe it's also open to update in the later stages. When capturing human curiosity, we do have like a bunch of like chatbot-like channels. We check what people ask on Google search, Bing search, these engine queries. We check what people ask on Quora. And also what do they ask to language models. So we have all these data and collect a set of 13.5K questions on curiosity-driven natural questions. And actually the good news is that 42% of natural questions are querying about something causal. So as I mentioned before, that we are also really impressed at what type of words hint a causal question, that the models should be alert. Whenever they receive these words, they should relatively activate the causal reasoning module. And also here's a list of human skills, human cognitive skills needed for causal questions, such as whether it's something about remembering, something about understanding, application, analysis, and so on. So we map this to this curiosity data set that we have on causal questions and checked that amongst the non-causal questions, more than half of them are about memorization. Among the causal questions that the user raised, 9.5% are memorization, and so on and so on. So there's also a strong type, like strong portion of application. Maybe there are existing mechanisms or existing insights we know, but we need to apply it in this case, and so on. Also, we checked how GPT-4o performed on these causal questions and find that they usually struggle in certain cases, especially about forecasting things into the future. They do very well in questions that require knowledge lookup. Either they already know or they can do it after a base search. However, also another thing is they have very verbose answers, trying to hit all the keywords and frame it in a little bit less efficient way. And also, as we mentioned before, when we receive a causal question, the curiosity dataset tells us 42% of the queries are related to causality. And then if we strongly focus on type 2 and type 3, causal discovery and causal effect estimation, then actually 53% of the questions can potentially be routed through this formal causal inference reasoning pipeline. Although this whole research agenda is really growing and might take a bit more to aim at higher accuracy. And also to enhance further accuracy, we have also been looking at things such as reinforcement learning and accurate middle checkpoints of language models. This work we wouldn't dive into detail, but we have a unit in the whole process about introducing formal verification framework in LLM-generated causal expressions that can help when LLMs try to formalize a query, like there might be a natural language description and we walk it through different steps of the query, then we have a formal engine behind to check whether each deduction step is actually correct or not. Yes, and the takeaways on this whole space before we move to the last paper. So a short summary for this whole thing is the space of natural causal questions shows the great potential of causality to chatbot AI assistance, and future work is needed to bring it even more scientific. And it will be very promising to compare LLMs as a knowledge base for causality and formal reasoning on these questions, especially if they will also be in conflict in some cases or just augment each other and in many different ways. Sort of finishing the whole previous batch of LLM causal reasoning, the last work we want to introduce is what does it mean for the recent rise of two things? One, reasoning models, test time inference, and also the other, multi-agent LLMs. Like now I still envision a lot of assumptions behind my previous work as there is just this one LLM, try to learn all the knowledge super well and apply them accurately. What about if there could be multiple LLMs interacting in the system? They can help each other, point out each other's flaw, or discuss with each other before deriving at the final solution. So we have a recent work revisiting the multi-agent debate as test time scaling, a systematic study of conditional effectiveness. Basically, as the title suggests, if we put multiple agents together, there might be certain conditions when it's effective and certain conditions when it's not. So the broad background we're looking at is for humans, sometimes when we solve complex problems, we host group meetings, we host discussions, we host debates. Same for multi-agent systems. There could be a complex problem that require multiple LLMs to discuss. And one example is if we receive a mathematics question on find all the real solutions to the equation, and then the different chatbots may be initiated as Alice, Bob, and Charlie. They might enter a multi-agent debate, MAD, for task solving. The round one, they might say they might propose their independent opinion. I think the answer is something, something. And then round two is they try to point out the error of each other's statements or endorse some solution steps by other agents. One example here by a 2023 paper, Du et al. Looks at how the agent's reasoning change after multiple rounds of debate. So you can see sometimes they are wrong in the early debates, and then in the last one, they're all correct. So this really sort of brings hope, but also some curiosity in on what condition does it work. Also, to bring in more context, debate can involve two agents representing opposing views to persuade each other before a judge decides. And also, we adopt the base version that they just come together and chat, and not specifically against each other head to head. And also to zoom out to the literature, we do see a problem of the whole field see multi-agent as a buzzword. And a lot of people say that maybe it's the next generation of improvement and so on. But really, why is a single agent not as good? If there is in human society, if there's an Einstein, I don't think maybe 3 random copies of us can debate and still win that opinion in certain cases. So we really want to see, is multi-agent effectiveness really a thing? Or how can we distinguish key features from a self-play reflective single agent versus the impact of multiple agents mixing together. So there are a lot of recent work looking at like sort of if multi-agent debate is the answer, what's the question, or different motivations here. So we look into MAD as a test time scaling, which is a term in recent LLM development. So basically, what people do is that LLMs has a pre-training stage, fine-tuning stage, RHF stage, where they update their weights. But now we're talking about all the weights are frozen, and we just let it run inference mode for a long time. Can we still improve the answer we get? That is what's called like test or inference time scaling. Let it run for a whole day, debating with each other or other agents. Can it be better at solving math Olympiad questions? So, and also there are scaling in terms of sequential scaling and parallel scaling, a lot of work from OpenAI, DeepMind, and so on. And also, if we have a graphical model of multi-agent debate, then the so-called parallel scaling is more like multiple agents do things at the same time and then aggregate. Some of the time can also be majority voting. If there are two C, one A, then we go with C, and so on. If it is about sequential scaling, it's more about an LM go through different steps and then run feedback, self-reflection, and so on before deriving at the final answer. And then the MAD is the general form MAD is a mixture of parallel and sequential scaling method with diverse exploration in terms of like the lines should be as large as possible, separate thinking lines, and hopefully they don't contaminate with each other. So there are certain rewards to encourage how diverse their language or opinions should be first in the first step. And then go to collaborative refinement, which is a property of the quality of their discussions and debates. Then, like in the stage 1 of diverse exploration, also there are multiple choices to make it diverse, such as maybe you can have a combination of different models, Llama, Claude, GPT, Q1, other things, which has different pros and cons. And then the other example is about initiating to different personas. Maybe here's a good psychologist, here's a good statistician, here's a good astronomist. Can we mix all these expertise together to make the debate more fruitful? And then in the collaborative refinement stage, it's more like all the previous stages are put into the context window of the next round of discussions. So in the end, you really see a massive input to models' next step generation. We run experiments targeting at 3 different research questions. The first one is, how does the task type differ for MAD versus self-agent effectiveness? The second is, what about the difficulty level if we put a very complicated math task versus a simple one? Or the model scale, the size of the model, does it change the answer of should I use multi or single agent? The third question is the impact of mixing heterogeneous agents from various developers versus homogeneous, like all ChatGPT and so on the MAD performance. Bring this forward, we do check the task. We actually check 2 types of tasks, one mathematical reasoning, one safety reasoning. For the specific context of this audience, we zoom more into mathematics reasoning, aiming to check how well MAD explores the solution space and collaborates to solve math problems that require complex step-by-step reasoning. So here, for example, on the case of homogeneous agents, that changing the models into multi-agent framework does not consistently outperform parallel sampling with self-agent. And also, but there are still some benefits coming from it. Namely, MAD relatively demonstrates clearer benefits, especially when the problem is more difficult. Moreover, if we look at the sequential scaling, namely like letting the model have a long reflection line and so on, MAD actively corrects errors. And unlike self-refinement, it makes it effective at high task difficulty when only a few initial agents are correct. Another qualitative example, if we extract model's reasoning process here, we can see that initially there's only one correct answer, and with self-consistency, one cannot catch this correct answer, and therefore it has just like multiple iterations, and really we see a divergence of, in some cases, like let's say like now what we see in round one is more like we run this thing in parallel and give different answers, and actually 55 is the correct one, all the others are wrong, but the model just like provide 4 independent solutions. And then in the round two, what it does is like in the collaborative refinement of all these 4 agents, they refine each other's answers and let one correct solution guide the process towards the right answer. So the 55 really got more endorsement across the 4 different reasoning paths. And then here, the takeaway one is that self-consistency excels, like trying to enforce self-consistency excels as math reasoning, but MAD gains a relative edge on harder problems via collaborative refinement that one self-agent might have certain blind spot on. Moreover, MAD is relatively more beneficial on challenging tasks, especially when we use a smaller model to deal with a task that's a bit above their capability scale. And also, like the second takeaway is that smaller models benefit more from MAD than parallel scaling on hard math tasks. As we see diverse exploration, as we see the diverse exploration process, we also bring in like the question of how does heterogeneous agents help? Basically, such exploration generally shows no clear advantage over the best single agent in math, no matter like the type of combination, let's say Q1 plus llama, Q1 plus gamma, and so on. So basically, we say that MAD for heterogeneous agents perform near the agent's harmonic mean, showing certain limited gains from diverse exploration in math reasoning. But we are also yet to scale this up on more challenging tasks and also more frontier models. So this is more like we raise the question and mention that all these conditions should be checked. And the key contributions on this line of MAD work is that we identify key features of the vanilla MAD, collaborative refinement, and diverse exploration. We investigate how these features provide benefits compared to test time scaling with a self-agent, and also explore self versus MAD across task types, difficulty levels, model scale, and agent configurations. So we have lots of community work in line with the research, sort of accompanying the research. Starting from 2021, a lot of workshop on NLP for positive impact. And also like in the last NeurIPS, we actually had 2 dedicated causality workshops. One on causality and large models, the other on causal representation learning across all types of data in general. And also next year, 2026, in April, we got successfully accepted at a Dachstuhl seminar on causality and LLMs, where we will invite lots of frontier causality / LLM researchers to discuss new frontier questions in the domain. And also all the work are supported by my brilliant mentors, mentees, and collaborators from different organizations. And we welcome any questions. Thank you. Yes. Yeah, totally. I think this is a great suggestion. And also, you raised the right example of economics where people actually can have different views and double check the assumptions. And maybe one community like a certain type of assumption, the other community doesn't. So we do think that multi-agent system is especially helpful for divergent views in a domain. Yeah, so this would be very helpful. And then uh, maybe it's also a domain related questions, maybe in healthcare or other domains. There could be a more well formalized problem, and the solution is more well known versus in others. It's more about, given this application, how to exactly apply it, what assumptions are satisfied, what is violated, are we happy with this choice of method, and so on. Yeah, really great question. Yes. This is a great question. Yeah, in human groups, and also in LM discussion, maybe the last suggestion has a recency bias. It's really, and it also needs to be separated into two cases. Like, do we want it to be very human-like, which will even encourage maybe interruption systems? Maybe some people speak a little bit, and also like, is it round robin or like whatever model that has a stronger opinion speak out first, and that has a that changes the communication atmosphere. Yeah, I do think there is value in separating a very clear mathematics or STEM domain versus a more like a social cultural discussion on where to go for dinner. If I plan a day in San Francisco, how to arrange the like a travel plan and so on. So I feel like there it's more about diversity, and maybe the first person who's speaking human setting and the last LM who speak in the M setting will have a stronger influence. Hopefully in math related, STEM related discussion, it's more like mapped to grounded topics, and or maybe we can even have certain checkers. At least for math, there are lean and other verifiers. Then which model is really correct should be leading the discussion. Yeah. Thanks for the question. Yes. Do you mean like if there is a further step on the models can suggest new experiments? Yeah, totally. So I think it would be super meaningful to add in interaction systems. We actually also meet with this thing in statistical consulting because the customer also come or user come and present their existing CSV data, but they have the power to collect new data. Yeah. Yeah. Mm-hmm. Mm-hmm. Right. Totally. And I think here it's more like maybe the experiment with the strongest power to demonstrate causality is this. And then the current experiment is that. And the model should show the difference and suggest some minimal edits, or maybe given the budget, what's the most informative decision to run. Yeah. And it has some Bayesian optimization there in terms of like, given the experiment, what do we expect the causal graph, or given the causal graph, what are the distribution of experimental results to check. So it will be a very meaningful topic to make it interactive. Maybe this question first and then that one. Yes. Mm-hmm. I think there are various opportunities for inference time agents to increase their performance. I guess Kyle's talk on data was originally targeting at when the model weights need to be updated. And then, like, the more data refines their decision to be more accurate. Here, it could be that if we want the model to do maybe a very specific domain, like nuclear physics, and then like feeding a lot of related information, will gear the power, like sort of guide the model into the distribution of this science. So I do think there will be improvement, and therefore these like super long context window models will have a stronger promise in this field. Sounds great. Uh-huh. Awesome. This is a great question, very forward looking, and also like sort of making the community ponder what's the right direction. I do think that there are two intertwined aspects in it. One is user interface design. The other is our belief in the fundamental technical breakthrough of them. On the user interface design, even there is this MAD set up multi-agent. We see at least ChatGPT or Claude. They let the model think for a while, but don't exactly tell you the thinking trace. And on the surface, the users say input, output, done. That's one choice. And then on the technical level, I think there is a question about if we fix the model to be the current capability, what do we choose? And also for researchers, what's the next improvement direction? So fixing the model to the current capability now, 2025, June, then it's more of a choice of do we want more reliability, but more human curated engineering effort, but we can comfortably present it to human scientists as a tool? Or do we want like language models generate more diverse results and just let everything be in the prompt and don't constrain it to call the code and so on? And also forward looking, I think the suggestion that was just mentioned about data scaling, that has a hope on increasing this. So the second type we call end-to-end reasoning. So the humans don't intervene and we don't go to more like grounded steps and let the language model do all the tasks. Then we need a lot of data. Hopefully, and also one way to generate such data is actually by synthetically constructing all the steps and then make the models walk through them. Yeah. And I think in general for math and physics, models do face problems in that the exploration space is very large. It's not about like maybe the customer raised a complaint on Uber and like they try to resolve it. But in math and physics, like each step has so many variants and also the knowledge base is super wide. So I do see these two lines of research will both survive for quite a while until there's a huge new release. Yeah. Thank you for the question. Maybe one last question? Yes. Yeah, this is a great question. I think it especially fits the case when maybe it's a bunch of earlier generation or smaller models and the leader is more performant. Like let's say maybe the lead is Claude Opus 4 and then the smaller models are Llama 4 or Llama 3 and stuff. Then the leader signal will make the next generation of the smaller models to perform better. However, if our research question is about if we can already access everything, frontier models, then how to still push the boundary of skills they can achieve. Then if we already have a good judge model, then it should become a doer model to solve the question. So maybe judge the quality of an answer would have not necessarily simpler complexity than solving the question. So it's still there still needs to do some work on task type and the exact model type of skill and so on. Yeah. That would be a great next step. As you mentioned, like there is not strict capability difference. Maybe like there's not strict capability levels, one being the subset of another, but maybe they have different skill distributions. Then they would complement each other's expertise. Thank you for all the questions.